So this is now the fourth module, okay, under part 8. So here we're going to discuss molecular spectroscopy via UV-Vis absorption and luminescence. No? So as we mentioned earlier, the manner by which molecules absorb electromagnetic radiation is a bit different from atoms. No? Sa atoms, simple lang yung energy levels mo. No? Yung mga 1s2, s2p lang yan. But for molecules, you have to consider the molecular orbitals, no? And the nature of the chemical bonds. No? So these are the basis for molecular spectroscopy. Okay, so for the use of UV-Vis radiation, this actually interacts with the valence electrons, no, in the molecular orbitals, no, of your analyte. So here we're going to discuss the yung general concepts, no, ng UV-Vis absorption and luminescence spectroscopy. So as we mentioned in the beginning of the lecture on interactions of electromagnetic radiation with matter, for molecules, no, so, yun yung analyte natin for molecular spectroscopy, the energy of the electromagnetic radiation will have different effects on your molecular analyte. Alright? So it has something to do with the energy, no? Yung degree or yung level of energy that a particular region of electromagnetic radiation has. Okay, so for example, no, if we look at the visible and ultraviolet region, the energy associated with this region is capable enough, or powerful enough rather, to induce electronic transitions, no? Particularly electronic transitions for the valence electrons. So if you remember from your general chemistry, valence electrons are the outermost electrons, no, in a given molecular orbital. Okay? So valence electrons yung nag-undergo ng electronic transition. Now, if we go towards the lower wavelength, say X-rays, so X-rays are more energetic compared to your visible and ultraviolet radiation. So instead of just inducing electronic transitions for the valence electrons, for X-rays, it can induce electronic transitions in the inner core shell electrons, no? Inner core shell electrons. So nandoon siya. Ano may inner core shell? Ito yung shells or orbitals na malapit sa nucleus. Okay? And for you to penetrate that deep, no, for a given analyte or compound, kailangan mo na mas mataas na energy level. Okay? Well, if we go further down, gamma rays, so we know gamma rays are very, very energetic. Okay? What it can do is it can already change nuclear configuration, no? So pwede na ma-break yung nucleus ng atom, no? Ito na yung realm ng radiochemical techniques na tinatawag. Okay? Now, kung doon na tayo sa kabila, longer wavelengths, no? So we start with infrared radiation. Alright? So for infrared radiation, the energy is not strong enough, okay, to induce electronic transitions, no, for the valence electrons. But what it can do is yung tinatawag nating vibrational transitions, no? Now, at the molecular level, vibrational transitions are basically you are inducing vibrations, no, between molecular bonds. Okay, so that's the basis of infrared spectroscopy, no? Kaya ang generic term dito ay yung vibrational spectroscopy, no, yung tawag nila dito. Okay? Microwave radiation, longer wavelength compared to infrared, so lower energy. Okay, so what it can do is basically vibrational spectroscopy into actually, no? But basically what it does is a change in orientation. Okay. Now, if we go further down, NMR, nuclear magnetic resonance spectroscopy, uses radio waves. No? So, very longer, no? Very much longer na electromagnetic radiation, so much lower than yung energy. So, it's not capable of inducing electronic nor vibrational transitions. But what it can do is yung tinatawag nating rotational transitions. No? So, what it does is that it changes the spin, no, of the nucleus, no, yung kung proton NMR yan or carbon 13 NMR, no, yung spin ng nucleus, but take note between a chemical bond, so kailangan bonded yung ating particular atom of interest. Okay. ESR, this is electron spin resonance spectroscopy. Kadalasan sa inorganic chemistry nag-uusapan ito, no? This is a powerful technique for studying intermediates ng chemical reaction, especially yung nature ng mga radicals or yung mga transition states, no? So kung medyo babasahin nyo ng konti si McMurray or si Klein dun sa mga sections on intermediates or transition states, makikita nyo itong technique na ito, no? Kasi ito yung isa sa mga confirmatory techniques na nagpapatunay ng existence ng mga ganoong transition or intermediates, no, for a given organic chemical reaction. So basically, for electron spin resonance, no, instead of changing yung spin, no, ng nuclei, ito nagkakaroon ka ng changing spin ng electron, no? So na-observe siya using ESR. So we will not deal with this for analytical chemistry. Okay, so you just need to take note, no, anong parting words natin sa slide na ito. The higher the energy of the electromagnetic radiation, the deeper, no, or the more intense yung effect niya doon sa ating molecular analyte. Alright. So, UV spectroscopy is used for the analysis of organic compounds. Inorganic species, so inorganic species can also be analyzed, no, using UV-Vis spectroscopy. So, ano yung mga inorganic species na UV-Vis active, no? So, yun dyan yung mga nitrates, no? Nitrites, no? So, these inorganic ions can be analyzed, no, using UV-Vis spectroscopy directly, or even charge transfer complexes. Okay, charge transfer complexes, no, such as you're familiar with copper ion, no? So copper ion appears to be blue in solution, but in actual, so kung blue siya, ibig sabihin it absorbs visible radiation, no, visible light. However, it's not actually copper ions, no, that absorb radiation, but rather it's the complex, no, yung tetraaquo copper 2 complex, no. So this is an example of a charge transfer complexes, no. So later, or kung babalikan natin yung experiments natin noon, no, one example of a colored or a visible light absorbing charge transfer complex would be your iron phenanthroline complex, no. So if you just have iron, no, if you want to analyze iron as your analyte, although colored ang iron, no, in aqueous solution, medyo may at higher concentration yellow, no, yung ferric form, so medyo yellowish, but at more dilute concentrations, the intensity of the color is very weak. All right, so to be able to more sensitively detect iron 3, you can analyze iron 3 based on its reaction with orthophenanthroline, no? So yung iron phenanthroline complex, 110 phenanthroline complex, no, which is parang reddish orange yung kulay ng complex na yun, no? So charge transfer complexes. Okay, now important term tinatandaan sa UV-Vis spectroscopy, it's not actually the whole molecule per se that absorbs UV visible radiation. Okay, but rather the absorption of electromagnetic radiation occurs more strongly doon sa tinatawag nating chromophores. Alright, so the chromophores, okay, are the functional groups that absorb in the UV and visible regions, no? So as you can see here, ano yung mga example ng functional groups, no, that absorb UV-Vis radiation. So you have your carbon-carbon double bond, carbon-carbon triple bond, mga alkynes, no? You have yung mga azo group, okay, azo group. You have your carbonyls, nitro, what's this? Ester group, amide group, nitro, nitroso, aromatic, etc. So, anong papansin natin? These are functional groups that have usually, no, have pi bonds, no? Pi bonds pala, no? Pi bonds. So, the nature of these bonds, no, in terms of energetics is that the energy difference between the, say, the pi bonding, and then the pi star antibonding levels, no, medyo magkalapit, no, in such a way that UV-Vis energy, no, UV-Vis radiation is enough to excite electrons, okay, towards those higher molecular orbitals, no, or higher molecular energy levels. Okay. So other terms, no, in UV-Vis spectroscopy, so you also have oxochromes. Okay, so oxochromes are those functional groups that do not absorb UV-Vis in the UV-Vis region. No, perhaps the absorptions as other EMR regions, but they have an effect of shifting chromophore peaks to longer wavelengths. No, ano ibig sabihin nitong chromophore peaks, no? Yung lambda max, no? Pwede tawagin lambda max. So, yung lambda max for a particular, corresponding to a particular absorption of a given chromophore, in the presence of these oxochromes, pwedeng malipat, no? There will be a shift, okay, in the wavelength of absorption, okay? So, in general, increasing the for conjugated compounds, no? So for conjugated compounds, as you increase the conjugation length, alright, so ibig sabihin yung gaano karami yung pila-pilang double bond, single bond, double bond, single bond conjugation. Alright, so ano effect nito? Increasing the conjugation also increases the absorption, no, with the additional effect of shifting, no, the wavelength of absorption towards longer wavelengths. Okay, so what does it mean, no? If the wavelength of absorption shifts towards longer wavelengths, it means that the molecule is more the molecule absorbs, no, the radiation more easily, no, compared to those that absorbs at shorter wavelengths. Okay, so explanation ito is more of quantum mechanical, no, if you've dealt with ito, particle in a box, no, and then not particle in a box, no, yung two-dimensional, no, particle in a two dimension, no, it actually isang application nun, no, or isang paggamit nun in explaining things is yung effect of conjugation dun sa absorption ng molecule sa visible range. Alright, so when the oxochrome, no, or whatever parameter na or substance na hinalo mo sa analyte mo causes a shift of the lambda max to higher wavelengths, you call that your bathochromic shift or red shift. Vice versa, if the oxochrome or whatever parameter or substance you add to your analyte causes the lambda max to shift to shorter wavelengths, you refer to that as your hypsochromic shift or blue shift. Alright, so as we mentioned earlier, the energy levels wherein your electrons transition during electronic transition for molecules, we don't talk about 1s, 2s, 2p, no, orbitals. No, those are atomic orbitals. Okay. So for molecular compounds, no, molecular species, organic compounds, one way to describe these transitions are in terms of their molecular orbitals nga, no? So yung sigma and pi bonds. So, well, you actually studied this, no, in organic chemistry and even in inorganic chemistry, no? So you're familiar now with your sigma bonds. Alright, so sigma bonds refer to the head-on overlap, okay, between atomic orbitals that form your molecular bonds, no? Whereas your pi bonds ay yung sideways overlap, alright, of your atomic orbitals, no? Usually your p orbitals, no? P orbitals form your pi bonds, no? Yung parallel, tama ba? Yeah, parallel p orbitals, no? In the given atom. Okay. Now, of course, you have your bonding molecular orbital and their pair anti-bonding molecular orbital, no? Signified as your star, no? Yung sigma star and pi star, no? And of course, if your atom contains lone pair of electrons, no? These lone pair of electrons are non-bonding electrons. Alright? So the energy level is actually kapantay, no, ng energy level ng individual atoms kasi nga non-bonding ito. Alright? So these are now your molecular orbitals. Okay? Now, similar to the discussion on atomic spectroscopy, no? Dito, so kunwari, if you have an electron, say, in this particular bonding sigma orbital, alright? If you allow this molecule to absorb electromagnetic radiation energy, no, corresponding to this difference, no, in energy level between the bonding and the anti-bonding pi orbital, okay, then this is what we call a pi to pi star transition. And this is a common transition for organic molecules, okay, that contain pi bonds. Alright? Well, that's the reason why very commonly molecules that contain double bonds, triple bonds, or aromaticity tend to usually absorb UV visible radiation, no? Because the energy difference between the pi and the pi star are not that big, no? The energy difference. Now, n to pi star or n to pi star relatively has smaller energy gap, no? Or energy gap between the energy levels. And this type of transition, n to pi star, is common for molecules, no, bonded or organic molecules with hetero atoms. So ito mga hetero atoms, carbonyl, amines, amides, no? So you would expect this type of transition for those molecules, no? If you look at this one, no, sigma to sigma star transition, the energy level is very, very high, no? And this is the reason why you don't expect pure alkenes, okay, to absorb in the UV-Vis region. So what I wanted to do for this topic is to read again, no, the PowerPoint lectures given to you for Instru 1, or you can read more about this in your textbooks, no? Which functional groups will exhibit the following type of transition. Okay? Now, daanan natin dito. Now, for luminescence spectroscopy or fluorescence spectroscopy, pabaligtad, no? So, after absorption, so for example, no, n to pi star. transition, no? So after the electron is excited to this particular energy level, no? After relaxation, babalik siya doon sa original orbital niya. And if this is accompanied by the emission of radiation, then you have fluorescence, no? Or phosphorescence, no? Whichever route, no? Yung dinaanan nung yung electron. Alright? So, some examples of the spectra. Alright? Spectra of your different organic compounds, no? Common organic compounds that do absorb in the UV visible range. So you have here your beta carotene, no? You know, beta carotene is a highly conjugated molecule, no? It's actually colored, no? Kulay orange yan. Okay, so the lambda max, as you can see here, is around 450 nanometers, no? Which corresponds to the color blue. Tama ba? Yeah, no? Medyo bluish na yung end ng kulay na ito. Okay? And we know for a fact that yung the color of the solution or the wavelength, no? Or the wavelength nung color nung isang solution or isang compound, yung lambda max would be the complementary color. Alright, so if you remember your color wheel, no? So this is the way I usually construct yung shortcut color wheel natin. So you have red, orange, yellow, blue, sorry, this is green, no? Green, blue, violet. Alright, so beta carotene is orange, no? Medyo orange yung color niya. And as you can see, the lambda max falls under the blue color, no? So complementary colors. Okay, so you also have caffeine, no? Caffeine, given this molecular structure, has a lambda max at around 270, so UV range, no? And even acetone, no? Which is a colorless compound. Well, caffeine is also colorless, no? So even acetone, no, has its corresponding absorption at around 270, which is due to this carbonyl functional group, no? By the way, this particular spectra, ang y-axis mo is the molar absorptivity, alright, epsilon. So remember that the molar absorptivity is actually a measure of how capable your molecule is with regards to absorbing electromagnetic radiation. Alright, so the higher the molar absorptivity, it would mean that the molecule is more absorbing. Okay, more absorbing, no? Towards the UV-Vis radiation. So as you can see here, even if acetone can absorb UV visible radiation, its molar absorptivity is relatively lower compared to the other examples here. And well, you can recognize here why. Because it only has that carbonyl functional group, okay, that can absorb UV-Vis radiation. Whereas for the other examples, no, for example, aspirin, it has what? Aromatic rings, no? It has the carbonyl for the ester group and the carbonyl for the carboxylic acid group. So this can contribute, no, to the absorption of electromagnetic radiation. Okay, so next you have your luminescence spectroscopy. So again, this refers to the measurement of the intensity of the emitted radiation. Okay, so well, we already discussed this, no? That once the electrons are excited due to the absorption of radiation, after some time, it will go back to the ground state energy level, no? And this can actually sometimes, no, this will be accompanied by the emission of radiation. Alright, so types of luminescence, no? So you have your fluorescence, phosphorescence, and chemiluminescence. So we already discussed this, no? So fluorescence and phosphorescence, the main similarities is that the molecule is excited by a radiation source, no? So merong ilaw, no, that excites your analyte, okay? And then during relaxation, it emits radiation, no, in the form of fluorescence and phosphorescence. Again, the difference for fluorescence, direct, no, after excitation, once your electrons go back directly to the ground state, it already emits the radiation. Whereas for phosphorescence to occur, your electron will first undergo intersystem crossing, no, from the excited singlet state towards the excited triplet state before it can go back to the ground state, no, ground state. All right. For fluorescence, no, this is an interesting call this phenomenon, no, for fluorescence, no. So this shows you, this is the excitation spectra. All right. So basically, the excitation spectra is the absorption spectra for your molecule, and this is the complementary emission spectra. No? So this shows you the emission, the behavior, the profile, rather, no? For the emission, the fluorescence emission. And as you can see, they are mirror images of each other. No? Number one, they're mirror images of each other, and another that you can observe is that for the in general, no, the emission spectra occurs for longer wavelengths, no, longer wavelengths compared to your excitation spectra. Okay, so bakit, no? The emission spectra occurs at longer wavelengths because some of the energy of the energy absorbed by their molecule was already released via non-radiative means. So remember, di ba, competing process yan, no? So hindi yan maiiwasan, no? So some of the energy previously absorbed during this excitation event were released via non-radiative means, no, internal conversion, vibrational relaxation, etc. So that's one reason why the emission spectra occurs at longer wavelengths, so meaning lower energy. But as you can see, they are mirror images of each other, all right, because the profile actually reflects the type of molecular orbitals present in your molecule. So ito yung parang fingerprint, no, ng iyong given molecule. Alright? So an important term in luminescence spectroscopy, or especially fluorescence, is what you call your quantum yield. Alright? So the quantum yield is simply the ratio between the rate constant, no? So again, process to, no? Rate constant of the fluorescence over the summation of all the rate constants of all the events that occur in your during electronic transition, no? During the relaxation process, no? So andyan yung fluorescence, ano nga yung internal conversion, external conversion. Okay, you have your predissociation constants, no, etc. No? So ito yung total events, no, yung described sa Jablonski diagram. So basically here, what we can say here is that the higher the quantum efficiency or the quantum yield, the higher the intensity, of course, no, of your molecule. Okay, and this is actually related to the instrument response, no? So for luminescence spectroscopy, kunwari fluorescence, no, the instrument response is the intensity of the fluorescence emission. Okay, and this is directly proportional, of course, to the concentration. Now, that's why if you're going to plot analyte concentration versus fluorescence intensity, it will be linear. Now, the proportionality constant here is, well, it contains the term on quantum yield, no? So, in analogy, quantum yield would be analogous to your molar absorptivity. Okay, so if molar absorptivity describes how well the molecule absorbs radiation, then quantum yield describes how well your molecule emits radiation, no, after relaxation. Amongst the spectroscopic methods, no, not counting mass spectrometry, fluorescence spectroscopy is the most sensitive technique, no, And why is that? It's simply because it's the analyte itself that gives you the analytical signal information. However, even though it's the most sensitive technique available, no, for spectroscopy, there is a what do you call this, limited number of molecules that could undergo fluorescence or sufficient fluorescence to be detected. No, why is that? Because there are several factors that determine whether a given molecule will exhibit fluorescence. Okay, so first is the structure. No, something about the structure of the molecule. No, so what are the features, structural features of a molecule that can undergo fluorescence? No, first, no, most molecules that have a high degree of aromaticity, high level of conjugation, tend to fluoresce. Okay, and why is that? Because the greater the capacity of the molecule to absorb radiation, it also means that it has a greater capacity to expel energy as radiation also. Okay, so that's what this means. No, that's why compounds that exhibit high degree of aromaticity and conjugation usually fluoresce. Another is heteroaromatics versus fused ring systems. No, so for example, you have here pyrrole. Drawing natin yung pyrrole. Sorry. Alright, so you have here pyrrole. Now, pyrrole being heteroaromatic in nature does not fluoresce, no? Does not undergo fluorescence. But if you have a fused ring system, no, such as the case of indole, alright, this molecule undergoes fluorescence. Okay? So ito magpo-fluoresce ito. Fluoresce. Okay? Yeah. Next, presence of halogens, no? The presence of halogens is a deterrent actually, no, for fluorescence. Okay? This is simply because the presence of halogens increases the rate constant associated with your pre-dissociation, no, yung KPD dun sa quantum yield formula natin kanina. Alright, so it usually reduces, no, the capacity of a molecule to undergo fluorescence. And also electron withdrawing groups, no, the presence of electron withdrawing groups sa mga aromatic ring systems reduces again the capacity of the molecule to undergo fluorescence. So these are the things that you need to look at in the structure. Okay, and then of course there is rigidity. Okay, rigidity, you know, one way to visualize this is in comparing these two molecules. No, first you have your biphenyl. Okay, now biphenyl, yan, so it's a two benzene rings, okay, attached on each other's carbon. Okay, biphenyl does not undergo fluorescence, no, even though it's highly aromatic, no electron withdrawing groups, no halogens present. Why? Because this bond here, okay, there is a possible vibration, no, between this bond, no, dito sa bond na ito. Okay, so this makes a structure less rigid. Okay, and when you have and when your molecule is more susceptible towards vibration, it increases the rate constant associated with vibrational relaxation, no, yung mga external conversion, no, vibrational relaxation, no, so nagkakaroon ng ganoong increase, no, possibility, no, towards non-radiative relaxation process. But if you convert this molecule, okay, and you attach a methylene group, okay, CH2 is called methylene, by the way, no? This is what we call now fluorine. Okay, And as the name implies, fluorine is actually a highly fluorescing molecule, no? And that is because the addition of this methylene group increases the rigidity of the molecule, no? Thereby reducing its chances to undergo vibrational relaxation. Okay? So what else? Temperature and solvent, no? Temperature and solvent, the lower the temperature, the higher the chances for fluorescence. And this is because, again, we are decreasing the kinetic energy of your molecule, okay, thereby preventing it from undergoing the release of energy by bumping with other molecules, no, in the solution or in the sample solution. Solvent, the higher the viscosity of the solvent, the higher the fluorescence becomes, no? And again, this has something to do with preventing your solute analyte from bumping with other molecules, no, in the solution. Okay? What else? Dissolved oxygen, no? Oxygen is actually a fluorescence quencher, no? It reduces the intensity of fluorescence. Okay, so if you want to measure fluorescence intensity, no, with the increase of fluorescence intensity as a factor for, or yeah, factor, as a function of the analyte concentration, then you want to remove dissolved oxygen. Okay. Well, something about dissolved oxygen. Typically, in fluorescence, this is your plot, no? So in concentration of the fluorescing analyte versus the intensity of the fluorescence, you now have there the a linear curve. Okay. Now, vice versa, you can actually use fluorescence to measure the concentration of a quencher, such as your dissolved oxygen. So how do we do that? First, you have a fluorescing material, okay, na constant yung concentration. Alright? So, ibig sabihin, constant ang concentration nan, okay, so fluorescing material, fluorescence intensity. So, since constant yung concentration ng different solutions na yan, you expect it to have a flat profile. Okay? Now, to analyze a quencher, what you do is in the separate solutions of this fluorescing material, you add increasing amount of the quencher. And what happens? No? What will happen is that you will have a negative slope corresponding to the increase in the quencher concentration. And this will also follow your linear curve, no? Proportional pa rin yan, okay? Yeah, no? Sorry, pero albeit ano siya, no? Inversely, no? Kasi you have a negative slope. Alright? pH also affects the fluorescence, no? Let's remove the other writings here. Hindi ko mahanap yung function na mabubura siya agad lahat. Okay, maybe that's enough. Alright, so pH, why? Because this affects molecules that do undergo fluorescence but has a tendency to dissociate, okay, with pH, no? So for example, if you have aniline, for example, as we mentioned earlier, for UV-Vis absorption, the manner by which aniline will absorb radiation would be different for that of anilinium ion. Okay, so if you have anilinium ion like this one, okay, so that will be different, and hence the manner by which anilinium ion will fluoresce, no, expected to fluoresce, will be different from that of aniline. Actually, anilinium ion is non-fluorescing. Okay, it's non-fluorescing. Why? Because the positive charge on the nitrogen makes it an electron withdrawing group, no? And sabi nga natin, if you have an electron withdrawing group, it decreases or disables yung fluorescence ng molecule natin. Okay? And finally, no, of course, no, the concentration of your fluorescing species, no, as what we've shown earlier, there is a direct proportionality, no, between fluorescence intensity and analyte concentration. Alright, although we are saying that the fluorescence intensity versus concentration plot is indeed linear, this is actually true only at low concentrations, no, or at dilute concentrations. So if we're going to extend the plot, no, between fluorescence intensity and analyte concentration, it looks something like this, no. So yung linear portion is towards the lower concentration range, no. And why is this, no? There are two factors that affect your uh, FC plot linearity. The first one is self-quenching, no? And this is due to the increased tendency in collision between excited molecules, leading to radiationless transfer of energy. So obviously, no, at higher solute or analyte concentration, the solution becomes more crowded with the analyte. So there is also an increased chance for your excited molecules to collide with each other, no? Hence, leading to a radiationless energy transfer, no? So bababa yung fluorescence natin. And another is yung tinatawag na self-absorption, no? So for self-absorption, this occurs when the wavelength of emission overlaps with the absorption peak of the molecule. So there are some molecules that do exhibit self-absorption. So what happens is that the emitted radiation, instead of going to the detector, okay, not all reaches the detector, no? Some part of the emitted radiation is reabsorbed by the unexcited molecules in the solution. Okay, so this is self-absorption. So both of this will lead to this kind of FC plot, no? So in general, although fluorescence spectroscopy is powerful, no, very high sensitivity, okay, its usability is for dilute concentrations only. Alright, so other related techniques to your fluorescence spectroscopy would be your phosphorescence and chemiluminescence spectroscopy. So for phosphorescence spectroscopy, so this is the sample container. Okay, it's important that you keep your sample solution during analysis in liquid nitrogen temperature. Okay, wherein the analyte is actually dispersed or dissolved in a very viscous solvent, no? And this is because, or sorry, this is to promote greater phosphorescence, no? I haven't seen actually, no, a phosphorimeter in real in actual laboratory setup, but usually phosphorimetry is used for trace analysis of some pesticides, no, or persistent organic pollutants, no? So for phosphorimetry, so if this is your light source, no, and then you have your, of course, your wavelength selector, no, there are shutters, okay, in between the sample container and the detector. Okay, so what they do, or actually calculate itong isang to, tama ba? Ay, hindi, meron nga yan. So what they do is this, no? So first, shutter number 2 is closed, shutter number 1 is up, and the purpose of which is to illuminate the sample. So remember, phosphorescence, parang charge mo yung sample mo with radiation, no? So you illuminate your sample for a certain period of time. All right, then afterwards you close in shutter number 1, and then you open shutter number 2, and this will now allow your illuminated sample to emit phosphorescence, and that phosphorescence to be detected by the detector. All right. Now for chemiluminescence, again, there is no light source needed, no? All you need to do is to mix the analyte with a certain chemical that will induce a light producing reaction, no? An example of which would be your luminol. If you're familiar with luminol, or even in nature, no? You have your reaction of luciferin, no? With luciferase enzyme. Okay, so this is an example of the time versus emission intensity plot, no, for chemiluminescence. So time 0 is the moment of mixing. All right. So here, what we get as your instrument response would be the maxima, no, the peak maxima, because it is expected that after reaching the maxima, the emission intensity will decay, no, because the chemicals are being consumed during the reaction. So we take this part here and we use this as your instrument response, no. Nonetheless, whether phosphorimetry or chemiluminescence, the intensity of the emission is directly proportional still to the analyte concentration, and hence you can express the relationship using a linear curve. Okay, so again, we're just going to upload the self-assessment problem sets later in our Facebook group page.